Hello everyone. In this video we're going to learn about the square root property, which is an extremely important property which will eventually enable us to solve any quadratic equation with real coefficients, even the ones that may have complex solutions. Before we do so, let's take a look at another important property we have previously discussed called the zero factor property. Which basically says if a product is zero, if a times b equals zero, then one of the two factors, either a or b, need to be zero. And this is an inclusive or, which means a is zero or b is zero or both, which is different from the way we normally use or in the English language. For example, when we say this evening I'm going to go to the theater or I'm going to go to the NBA game, we usually don't mean I'm going to do either this or that or both. We mean I'm going to do this or that, but not both. So that's an exclusive or. But here in mathematics, unless otherwise specified, when you see or, that's an inclusive or. So let's go ahead and recall how to use the zero factor property. So here's a simple quadratic equation: x squared minus 5x plus 4 equals 0. As you know, we can factor that as x minus 4 times x minus 1. The equation becomes that equals 0. And then now we apply the zero factor property with x minus 4 playing the role of a and x minus 1 playing the role of b. So we get either x minus 4 equals 0 or x minus 1 equals 0, which of course we can quickly solve to give us x equals 4 or x equals 1. Now we've already solved simple quadratic equations that can be factored once we set one side equal to 0 and get all the variables on the left side, or one side or the right side. The side doesn't matter as long as all the variables are on one side and 0 is on the other side. So those we know that we can solve using the zero factor property. Now, we can also use zero factor property for an equation of this type. Like, let's say we have x squared equals 9. Then we know that we can take 9 to the left side and make it x squared minus 9 equals 0 by subtracting 9 from both sides. 9, of course, we can write as 3 squared. So now we notice that we have a difference of squares. So we have the formula which will enable us to solve, factor such expressions. We know that f squared minus l squared equals f plus l times f minus l. So here f will be x and l will be 3, so we can easily factor that to get x minus 3 times x plus 3 equals 0, which of course gives us either x minus 3 equals 0 or x plus 3 equals 0 by the zero factor property. And we end up with x equals 3 or x equals negative 3. Of course, we had a property from the past which said if you take the square root of any number and square it, you get the number itself. Or more formally, the square root of a radicand squared gives you the radicand. And this will enable us to solve equations of this type even when the number on the right side is not a perfect square. So let's take a look at an example like that now. So here we can see an equation that fits that description. It's very similar, except notice that the 7 is not a perfect square. But that's not a problem. We can still move the 7 to the left side and come up with this equation. Now we're going to use the property we just discussed up here, and we're going to be able to write 7 as the square root of 7 squared. And we end up with this equation now. So now we notice again we have a difference of squares, so we can use the difference of squares factoring formula. So with f being played by x and the square root of 7 being played instead of l, we end up with x minus square root of 7 times x plus square root of 7 equals 0. Now we set each one equal to 0 by the zero factor property, and we end up with these two solutions: x equals square root of 7 or x equals negative square root of 7. Now, as it turns out, we encounter problems of this type quite often in both mathematics and related branches. So it would be nice if we had a property that enabled us to jump from this to the solution in a much quicker fashion. And that's where the square root property comes in, which we will introduce next. Okay, so now here we'll present the square root property as a theorem and proceed to prove it so that we can then use it safely from this point forward. So the statement is that if the x squared equals k, then x must be plus or minus square root of k. It's, when plus and minus are used as signs, we usually say positive or negative, but it actually rolls off the tongue a lot better to say plus or minus, so we say that instead. Otherwise, the real correct language would be positive or negative. So here we start with the given fact that x squared equals k. We go ahead and rewrite k as the square root of k squared, and we go ahead and move this term now to the left side by subtracting it from both sides, and we end up with this expression, which is the difference of squares. We proceed to factor it using the difference of squares factoring formula. Now we apply the zero factor property to these two factors. We end up with x plus square root of k equals 0, or x minus square root of k equals 0. Of course, solving this will give us x equals negative square root of k. Solving this equation will give us x equals square root of k. We usually write this in the compact form of x equals plus or minus square root of k. And now we have established the theorem. We have proven it. So from this point forward, when we see an equation of the type x squared equals k, we don't have to go through all this work like we did here, or like we did in the case of x squared equals 7. We'll just go ahead and use this theorem, given that it is a proven fact which we can safely use. We also have a more general version of the square root property, where instead of the expression being squared just being x, it can be a linear combination of x, such as ax plus b squared equals k. We can just, in that case, go through an exactly similar type of proof and end up with the fact that ax plus b must be positive or negative square root of k. And of course, what you need to keep in mind more than anything else is that the square root property, even though it's something we're formally proving here, it's also just common sense. Because notice that if you take the positive square root of k and square it, of course, you end up with k. So that means positive square root of k satisfies this equation. In other words, it's an x value that if you square, you get k. So there it is. And also notice that if you take the negative square root of k and square it, you also get k. So do learn the square root property, not in the just in the formal sense, but also the fact that it's just pure common sense. And same way here, you see. We can go ahead and proceed now to use the square root property in many different situations. So we're about to use both of these versions to solve a number of problems. And of course, in this case down here, we're saying some expression squared equals k. So what can that expression possibly be? Well, remember, there are only two items that if you square, you get k. Therefore, this expression that is being squared to give us k must be one of those two numbers right there, either positive square root of k or negative square root of k. So let's go ahead and look at some examples now. Okay, so here we're going to use the square root property to solve x squared equals 24. As always, I invite you to try this on your own first before you come back to see it, if you feel like you can do it on your own. If you don't, obviously you can watch one or two and then try to do the rest on your own, whichever works for you. So here, obviously, this totally fits the square root of property condition, which says if x squared equals k, that implies x must be positive or negative square root of k. So obviously we can use it here, so we can say x equals plus or minus square root of 24. And now we can go ahead and simplify this, because we always leave our final answers in the most simplified form in mathematics. So, and of course that's a simple problem to simplify. We just break it up into two radicals. In one we put the perfect square factor of 24, and in here we put the entire non-perfect square factor of 24. And of course we know that 4 is a perfect square factor of 24. In fact, it's the largest perfect square factor of 24, and that leaves us 6 as the rest of the factors which are not the product of the factors that are not perfect squares. And of course that's easy to see. If you break down 24, you get 12, 2, 6, 2, 3, 3, 1. There's only one perfect square inside it, which is 2 squared. So that one in here. And what's left is going to be the non-perfect square factor of 24 once you multiply it, and that's going to be 6. So we get x equals plus or minus 2 radical 6, and that's pretty much it. Now we can just write it as a solution set, which is the modern way we handle these things in mathematics. So we get negative 2 radical 6 comma 2 radical 6. Of course, you know that in sets, order does not matter. So here I could have put this first and this second, but normally we like to go ahead and write them in order from smallest to largest, simply just so that all our solutions will look the same way and they agree. All right, so in this next problem on the right, we have also a situation which is possible to solve using the square root property. So here, instead of x, we're going to get a equals plus or minus square root of 144. So we get a equals plus or minus, this time we know that 144 is a perfect square. So we get plus or minus 12, and that happens sometimes as well. And of course, you can easily check these by just taking your solutions and squaring them and making sure you get the number on the right. Here, obviously, if we take positive 12 and square it, we get 144. And if we take negative 12, quantity negative 12 and square it, we also get 144. So we know that it works. So here we're just going to write our solution set to contain negative 12 and 12. All right, as always, make sure you can do the simple problems on your own before we proceed. Okay, so in this example, we notice that it looks a little bit different, but remember, a quadratic equation normally has the form the ax squared plus bx plus c equals 0. Okay, rather than saying has the form, we should say can be put into this form, right? It may have other forms, but if it's indeed quadratic, you should be able to put it into this form. Now, notice that with these special types we're solving, the x term, or the first degree term, to put it formally, is missing. Well, it's not that it doesn't exist, it's just that b happens to be 0, so it zeroes out the entire what we call first degree or linear term. So in these types of situations where the x term is missing and you only have a square term and a constant, you should be able to use the square root property. It's just that sometimes you may have to get it ready for such usage. So the way we'll handle this is we'll go ahead and solve for x squared first. So we have 9x squared. We'll go ahead and add 25 to both sides to get 9x squared equals 25. Now we'll go ahead and divide both sides by 9. So we get x squared equals 25 over 9. Notice that now you're in the form of x squared equals some constant, right? So now we can apply the square root property, which says x must be plus or minus square root of that constant. So here we're going to get x equals plus or minus square root of 25 over 9. So now, of course, we know that square root of 25 over 9 is a nice, simple, rational number, and it happens to be plus or minus 5/3. And we can go ahead and write our solution set as containing negative 5/3 and 5/3, like so. All right, so again, if you ever wanted to check, that would be easy too. Just go ahead and take positive 5/3, square it, and multiply it by 9. We're just plugging into the equation. Wherever we see x, we're going to plug in positive 5/3. And we want to know if that minus 25 equals 0. And of course, 5/3 squared is 25 over 9. So 9 times 25 over 9 minus 25. We're checking to see if that's 0. Therefore, the question mark, because we're not asserting, we're checking. We notice that the 9's cancel out. And we end up with 25 minus 25. We want to know if that equals 0. And of course, 0 does equal 0. And we have verified it. Now you can do exactly the same analysis by plugging in negative 5/3, and you'll see that that will also make the equation true. To check, you always take the proposed solutions and you plug it into the original equation. All right, so here on the right, we're going to solve another one of these, which of course needs a little bit of prepping also. So we're going to go ahead and solve for x squared first. So we get 2x squared equals 1. Now we go ahead and divide both sides by 2. So we get x squared equals 1/2. So now we get x equals plus or minus square root of 1/2. And of course, we won't leave that like that because we know a simplified expression which has radicals in it should not have any radicals in the denominator. So we'll go ahead and realize that we can break that up as plus or minus square root of 1 over square root of 2, which is plus or minus 1 over radical 2, which of course we can quickly rationalize by multiplying the top and bottom of that fraction by radical 2. And we end up with plus or minus radical 2 over, now we know radical 2 times radical 2 is just radical 2 squared, which of course is just 2. So we get plus or minus radical 2 over 2. Now we can write our solution. Of course, those are values for x, and our solution set will contain negative radical 2 over 2 and radical 2 over 2. Make sure you can do this on your own without looking before you proceed. All right, so here we have a couple of more problems to look at. Definitely try them before you come back and unpause the video. All right, so here we notice that when we describe the square root property as x squared equals k implies x equals plus or minus square root of k, we didn't have any restrictions on k. So it works when k is negative as well. So we're just going to use the same rule. So we're going to get x, this touchy computer screen. So we get x equals plus or minus square root of negative 28. And we will, of course, simplify that. So we get x equals plus or minus square root of, this time we'll break it up into 3 radicals. We'll reserve the last one for -1. And we, of course, if we look at 28, we know that 2 goes into it 14 times, another 2 goes into it 7 times, and 7 goes into it 1 time. On the left, we have the prime factorization. We can see that there's a perfect square there, so we can put 4 in the first radical, the perfect square radical, 7 goes in the non-perfect square radical, and we have -1 in the last one. Notice that 4 times 7 times -1 is indeed -28. They have to all be under the radical, of course. So now we know that the square root of 4 is just 2, right? So we get plus or minus 2 radical 7. And we know that we always want to write the square root of -1 as I. And now we have it there and it is done. So we're going to write our solution set to contain -2 radical 7I and comma 2 radical 7I. Again, that's easy to verify as well. Let me just verify the first one for you. You can do the second one. So if you want to check, you can go ahead and plug in -2 radical 7I into the original equation and see if it turns it into a true statement. So we want to know if -2 radical 7I squared equals -28. Now -2 squared is 4, square root of 7 squared is 7, and we have I squared. We want to know if that's equal to -28. I squared, of course, we know is -1, so we have 28 times -1. So we get -28 equals -28. We can drop the question mark because we have verified it. It does make the equation true, so it works. Again, you can do the same with 2 radical 7I. All right, so for this problem on the right, we're going to go ahead and move the 14 to the other side. Remember, we want to isolate the x squared first. So we get -10 minus 14. So here we have 3x squared equals -24. We can go ahead and divide both sides by 3 now. So we get x squared equals -8. Applying the, now we're ready to apply the square root property, which tells us x must be positive or negative square root of -8. Again, we'll go ahead and break that up into 3 radicals. In the last one, we put -1. In the first one, we put the largest perfect square factor of 8, which we know is 4. Whatever is left goes into the next radical, which is 2. And we end up with positive or -2 radical 2I. And we can write our solution set as the set containing -2 radical 2I and 2 radical 2I. Notice that some people prefer to put this I next to the 2, and that's okay too because of the commutative property of multiplication. But pure mathematicians will prefer this because we have the standard complex form, which is a plus bi. So we like to write the b first and then the I. So either way is fine. That is not incorrect if you put the I next to the 2. Whatever you do, make sure you don't put the I under the radical. If you do that on a computer system such as my MATLAB, it'll definitely count it as wrong because we know I is already a square root. It's the square root of -1. So you don't want to put the I under the radical in any of these problems. And that should do it. So make sure, again, you can do this on your own before we go to the next screen. All right, here's the last two set of the last two problems we're going to look at. They, if you notice, are the more slightly more complex version where the expression being squared is not just x but some linear combination of x, but the rule is the same. Let me remind you, the more general version of the square root property said that if ax plus b squared equals k, that implies that ax plus b must be plus or minus square root of k. So we're going to apply this version. So here we're going to get that x plus 3 must be plus or minus square root of 144. So we get x equals negative 3 plus or minus square root of 144. Now we know that square root of 144 is a nice simple 12. So we'll go ahead and replace the square root of 144 with 12. Notice that when it turns out to be two nice integers like this, you shouldn't leave the answer like this. You should go ahead and work it out. So here we're going to consider what the plus case gives us and what the minus case gives us. So the plus case gives us x equals negative 3 plus 12. The minus case gives us x equals negative 3 minus 12. So on the left here we get x equals 9, and on the right we get x equals negative 15. Now, if you quickly check, and this you should do at least in your head, even if you don't do a formal written down check, right? So notice that if I plug in 9, I get 9 plus 3, which is 12, and when I square that, in fact, I get 144. Now, if I plug in negative 15, I get negative 15 plus 3, which is negative 12, and we know that if we square all of negative 12, including the negative, we do in fact get positive 144. So you can see that they both work. So here we'll write the solution set. As my usual habit, I'll go ahead and put them in ascending order, even though once again that is optional. We could have put 9 first and then negative 15. As long as we separate by comma, that would still be considered the correct answer. So here on the right we have another equation that looks similar to this, except notice we have a negative number here for k, and we had no restrictions on the value of k. K, as long as it's a real number, should work even if it's negative. So we'll go ahead and apply this general version of the square root property to get 2x minus 3 equals plus or minus square root of negative 24. Now we'll go ahead and isolate the x term, so we get 2x equals 3 plus or minus square root of negative 24. We notice that we can divide both sides by 2, but it might be easier if we simplify this first before we get any fractions involved. So we'll do that first. So we get 2x equals 3 plus or minus. We'll break that up into 3 parts, 3 radicals. We'll put negative 1 in the last one. The largest perfect square factor of 24 in the first one, and the product of the rest of the factors in here, which are not perfect square. So we know that means we need a 4 here, and a 6 in the next radical. Okay, this is not cooperating. Here we go. 4 here and 6 here. So we end up with 2x equals 3 plus or minus 2 radical 6i. Now we can divide both sides by 2 to get x equals 3 plus or minus 2 radical 6i over 2. Now this is an acceptable form for the solutions, but oftentimes from a purely mathematical standpoint, we like to write this kind of a solution, which is complex, in standard complex form, which means we'll split it up. So we get x equals 3 halves plus or minus 2 radical 6 over 2i. Now we notice that we can cancel out the 2's here, and so we end up with x equals 3 halves plus or minus radical 6i. And we go ahead and write our solution set as containing 3/2 plus or minus. Let's start with the minus, doesn't make much difference. Radical 6i and 3/2 plus radical 6i. Again, in the back of some textbooks, you may see the solution set looking like this: 3 plus 2 radical 6i over 2, comma 3 minus 2 radical 6i over 2, and that's correct as well. But again, we prefer this one because you can clearly see that these two solutions are complex conjugates, and from a purely mathematical point of view, we always prefer complex conjugate form. Notice that the last set of problems that we did, these are also complex conjugates. Notice this one you can write as 0 minus 2 radical 7i, and this one you can write as 0 plus 2 radical 7i, and the same goes here. These can also be written in a standard complex form with a 0 brought in. Now, also pay attention to the fact that when the complex number a plus bi is observed, we call a the real part of the complex number and b the imaginary part. In problems where the real part happens to be 0, as in all 4 of these cases, these numbers are called pure imaginary. So both of these problems have solutions that are pure imaginary. That means if you were to plot these solutions, they would all fall off of the x-axis or the real axis in the complex plane. And that should pretty much bring us to the end of this lecture. So make sure you practice these and be safe until we meet again.